Very good morning, students. In the previous lectures we have seen the design and other aspects of the reinforced soil retaining walls. In this lecture I want to explain the case study of the construction of very high retaining walls in India. I will go step by step on why the system was selected and how the materials were selected and what were the construction aspects, and then other associated factors as we go along. Brief history of the mechanically stabilized earth walls or just simply reinforced soil retaining walls are like this. The first wall was built at Ludhiana in the mid 1980s. That was basically an experimental type of case study that was proposed by Central Road Research Institute, and that particular wall was about 9 meters, and they used fly ash as a backfill, and they found that the cost economy is about 40 to 50%, because they were able to avoid the import of materials and so on. And at the present moment, over the past 25 to 30 years, lot of developments have taken place in the technology, not only in India, but even in other countries. And now we have reached such a state that most of the road over bridges in India that are built on the national highways, as a rule they use this technology of reinforced soil retaining walls for all the approach roads. And it is very common as we travel along the highways to see the walls of about 10 meters height, and a variety of reinforcement materials were utilized for different constructions. For example, the geosynthetics like the different types of geogrids, extruded and then woven and knitted type polymeric geogrids, and then the steel ladders, that is the welded wire steel meshes, then steel strips, and then polymeric strips, and then anchor systems, especially with steel strips with an anchor at the end to increase their pull out capacity. And both the soil and the fly ash are used as backfill materials. And till date the maximum height of the reinforced soil wall in India is about 45 meters, and that is the case study that I am going to discuss in today's lecture. And one project is currently underway at Sikkim, wherein the height of the support is exceeding 100 meters, it is about 110 meters. It is not technically a vertical wall, but it is a steep slope. And this particular picture shows the variety of the reinforced earth walls that were built in India. This picture shows the full height facing panel wall, wherein we cast the facing panel, and at the time of casting we put in some small short strips of the reinforcement at the time of casting, and then later on we attach the necessary length of reinforcement through some bodkin and other things. And here is a modular block wall, wherein the front facing is made of small sized blocks, and these are this is the wall built with the panels, each about 1.5 meters to 1 to 1.5 meter wide and about 1 meter height. And actually here we see another close up of the panel wall, and the reinforcement is a steel mesh, and here you can see the how the this steel mesh is connected to the front facings through these hooks and then this cross rod. And here we see an example of a steel strip being used as a reinforcement along with an anchor, so that the higher pull out capacities can be mobilized. And here we see a geogrid being used as a reinforcement layer, and in this picture we see the gabions, the stone filled metallic gabions used as facing elements. And here we see another example of a of a retaining wall with facing panels, but with polymeric strips. And so we can see that a variety of reinforced soil retaining walls were built in India. And in today's lecture, I will describe the construction of very high retaining walls, that is up to 45 meters, 44 meters to be very precise, that has not been built in India till date, and even in the world these walls will stand as one of the tallest. And this particular construction took place at the Ghat road leading to the to Kanakadurga temple at Vijayawada. This is the inset shows the temple, and this is at the top of a hill, and there is an approach road that was built in the mid 30s or 40s. Probably initially it started as a footpath, later on it got widened and made into a motorable road. And this particular strip, this is how the road goes, and then it winds around, and then it goes up to the temple. And there were two walls that were built along this stretch, a 22 meter high wall, and then along this stretch this is a 44 meter high wall. Is actually both of them posed a lot of challenges, mainly because this particular heights have never been constructed in India. More than about 15 meters have never been constructed. So this the back side of this Ghat road is all fully hillock area, hill, and a photograph of the overall site conditions is shown here. Is actually this is the road, and that is the hillock, and this is the bottom level of the road. And the purpose of this construction is to widen this narrow road, because the narrow road is so narrow that it was meant mainly for bicycles and scooters, and later on people started using cars. Then you have to squeeze through a very narrow opening, which is quite dangerous. Then after if too many people drive the cars up to the temple, there is no parking space. So that has to be also catered for in this construction. And here you see the narrow stretch of the road. Actually it is so narrow that not more than one small car can pass through, and this has to be somehow widened. You can see the conditions of the hill here. Is actually this hillock has a lot of problems, because there are too many joints and crevices, and frequently during the monsoon time huge boulders fall down because of the number of cracks that are there in the site. Then another problem that we have is just next to this is the major Krishna river, and so we cannot exceed our boundary beyond certain limit. So let me highlight the purpose of this construction. The purpose of this construction was twofold, that is widening of the approach road, as I have shown earlier. The purpose of constructing one of the walls is to widen this road, and another wall is to create a large parking area at the top of the hill, so that people can park their vehicles. And the schematic is shown here. Let us imagine that this is the hillock that we have, and then we want to create some extra space at the top, either for widening the road or for creating the parking space, and that space we will get only if we fill this area with some material, and invariably that material happens to be the soil, because the soil is plentifully available, and it is relatively inexpensive compared to other construction materials like reinforced concrete and so on. And of course the other material that we can think of is the pond ash or the fly ash, but there is not much of an experience in using pond ash for this height of construction. So, here at this particular place it is proposed to form this soil fill, so that we can gain this space, and the approximate height varies anywhere from about 20 meters to 45 meters. So, this if we can make this face as vertical as possible, we can gain the space without encroaching onto the other side. The main problem here is just to the right of this there is a busy national highway, and just next to that is the Krishna river. So, we cannot really think of extending our property boundary beyond this line. That is the major constraint. See, whenever we have a construction project, we should look at different alternatives, so that we can choose what is the best for our site conditions, considering the cost factor, and then the time factor, and then the practical construction aspects. And in this particular case, we can consider different options, like we can create a wider road or a parking space by blasting up the hill to create the additional space, but that is ruled out primarily because the fragile nature of the rock does not permit for controlled blasting, and also the entire area around the hillock is highly built up. There is too much population to take any risk of any flying debris falling into the neighboring habitated area. Or another possibility is we use a reinforced concrete retaining wall to that, say if we can construct a reinforced soil retaining wall here, we can backfill this with soil and gain the space, but that is ruled out because of cost considerations. Once again, it is very highly uneconomical, because even for a say for about 3 to 4 meter height of the wall, the thickness of the stem comes out to be about 300 millimeters, and for a height of 44 meters, the height could be as high as about 1/8 of that. So, it will be about 5 to 6 meters wide, and then it is mainly ruled out not only because of the cost factors, but the approach area is so narrow that we cannot bring in the concrete lorries to, and so it is very difficult. And then pumping in the concrete from a high height is also a problem, because that also we need to see how practicable it is to pump the concrete at very high heights. Or other possibilities, we build very high columns with reinforced concrete slab at the top, but then that is also very expensive, because the height of the column when it is greater than some value, you know that buckling will be a major phenomenon, and to control the buckling these columns have to be of very large size, then they need to be supported by some means, and that proved out to be very expensive, and it is not possible. And the simplest alternative is to go in for reinforced soil retaining walls. And among the reinforced soil retaining walls, one popular option is by using facing panels. These panels are about 1.5 meters wide to 1.5 meter, 1 to 1.5 meter height, but that is ruled out at this particular place, because this size of panels they weigh about 1.5 to 2 tons, and we need a crane, and especially operating the crane at a ground level is not difficult, but as the wall is progressively increasing in height, how do we move the panels to that height? That was a major problem. So, it is once again these panel supported reinforced soil walls are not possible, and so based on all these considerations, we have to choose the the particular type of facing panel and the system. And some of the anticipated problems that were thought about even before suitable system was identified. It has a very limited access to the construction site. Actually, it is, I will show you some pictures where there is a very narrow pathway and heavy rainfall, because this particular place Vijayawada receives about 1.5 meters rainfall every year on the average, and we should anticipate very large surface runoff from the upper reaches, because this is all a hilly terrain, and even if there is a very small drizzle, it results in very high surface runoff, and there is a limited space for mobility of the equipments, because as opposed to the construction of the ROBs, where there is a free opening on one side through which you can bring in the equipment. Here there is no such possibility, and because of that we have to think of some ingenious ways of construction, and the major problem is the large height of walls of this kind, which were never built in India. Then the hill slope itself has a lot of disintegrated rock with several joints and fissures, and then there are frequent boulder falls, at least once or twice a year it happens. So, we should design our system to overcome all these problems, and this picture shows the narrow access road, because this entire area is highly built up. There is one building here and then there is one building here, and this opening is hardly about 2.5 to 3 meters, which is too narrow for any large construction equipment to come through. And so, we cannot really think of moving a heavy crane or heavy lorry load of vehicles coming in here, because this particular wall is just nearly touching this building. So there is a great constraint on the space that we have at the site. So, this the reasons for the choice of reinforced soil option is the construction of the reinforced soil wall does not disturb the existing hillock, which is already very fragile. So, this because the construction of the reinforced fill does not impose too much of load, because we are only placing the soil, and then our facing panels or the facing elements are all very lightweight, and this reinforced soil wall, it can be constructed fairly steeply near vertical angles, and it can provide an additional 20 meter wide space over the existing 3 meter wide road, and so that is that's an advantage for us to create a very large parking area. And this geosynthetic reinforced segmental walls, that is the type of system that is proposed, is found to be economical all over the world and very fast for construction, and it does not require heavy machinery for construction. This is the most important factor that we need to consider, because we cannot bring any construction equipment. So, the site conditions are like this. The annual precipitation is fairly large, about 1.5 meters, and there is a good bearing stratum at a very shallow depth, and there is a rock at a shallow depth of about half a meter to 1 meter. So, that means that we do not have to go in for any foundation soil treatment, and the only problem is there is not much of construction fill that we can use at a nearby site, and there is a quarry at about 25 to 30 kilometers from the site, and there is it is a red gravelly soil that we call as muram, with about 30% fines, and the exact content of this soil, the gravel content, that is the particles coarser than 4.75 millimeters 39%, coarse sand about 5%, medium sand about 12%, fine sand 8%, and then the silt and clay is about 36%. And as we have already discussed, any soil with fines percentage more than 15% is not allowed as per the relevant codes of practice. So, it was proposed that we bring in this soil, but mix it with the river sand that is available to some extent nearby in 50-50 ratio to reduce the fines to less than 20%, and it was mixed locally at the site, and the plasticity index of the gravel soil is less than 6%, because the clay is not very active clay, and because of the sedimentary nature of this soil, the plasticity is not very high, because the main problem with the soil plasticity at this place is because of the height of the soil fill. Because it is very high, we should expect some compressions, the post construction settlements and compressions, and as we know from our consolidation theory that as the plasticity of the soil is increasing, the compressibility increases, the compression index is higher for highly plastic soils. So, it is very important that we use a soil that has a very good compaction properties, and at the same time it is not compressible in future. So, that is one reason why the fly ash or the pond ash could not have been used at this site, because it is not possible to compact the soil to very high heights. And the particular system that was adopted for construction is the use of modular block facings, mainly because it is easy to handle. One single person can easily handle these blocks, because each of these blocks they weigh around 30 kgs, and it is proposed to construct a tiered retaining wall instead of one full vertical retaining wall to almost 40 meters. Instead the tier system was proposed, mainly because it increases the stability, because we know that as we have a shallow slope the stability is higher, and similarly with by providing the berms or the tiers the stability is increased, and more importantly it provides some space for the staging. To construct upper reaches of the wall we need some base, and that base is provided by these tiers. And in terms of appearance and the aesthetics, the tiered wall looks much better, because we break the monotony of the wall and we can grow some vegetation on these tiers, so that in future this wall can be blended with the surroundings. And the type of reinforcement that was used, it is not a normal reinforcement. It was proposed to use very high strength polymeric composite, which has excellent strength and drainage properties. Up front it is anticipated that water is a big problem, because of the heavy rainfall and heavy runoff. We should expect some water to infiltrate into the reinforced soil fill, and once it infiltrates it should have a passage out of the soil, and because of that a composite is used. A composite is nothing but a combination of two different materials. In this particular case it is a combination of a geogrid that provides the tensile strength, and then a geotextile that provides an opportunity for the water to flow along and dissipate from the ground. And this the reinforcement that was used was was made of polyester fibers having tensile strengths in the range of 50 to 200 kilonewtons per meter, and the geotextile backing for this geogrid is made of needle punched non-woven polypropylene. It is a fairly thick geotextile. It is about 2.5 to 3 millimeters thick. and the design itself is based on several codal provisions because of the site conditions. For most of the designs, the BS 8006 was used for the static loads, that is for checking for the lateral stability and then internal stability, both under external forces and internal forces. And as we already know, the BS code does not talk about the seismic loads, and so the seismic load factors were taken from the Federal Highway Administration design guidelines only for the purpose of estimating the seismic loads. And the part of the reinforced soil walls built using modular blocks is better discussed in this the NCMA guidelines. That is, the NCMA is the National Concrete Masonry Association. They also have guideline for constructing the soil walls using the modular blocks, and the connections, especially the connection strength between the reinforcement layers and the modular blocks is better explained in this NCMA manual. So, all these three major design codes were utilized for design purposes. A tiered wall is something like this, and this is from the Federal Highway Administration guidelines, and there are different steps. Let us say that this H2 is the bottom tier, H1 is the upper tier, and the code says that if this offset is less than the 1/20th of the total height, then you treat it as one single vertical wall, and the internal rupture surface is like this. And if on the other hand, if the upper walls are so far away with so much of offset that the Rankine active rupture plane that is drawn does not interact with the upper tier, then we can treat both the walls as two independent walls, and then the design is based on our conventional systems, either based on the tie-back wedge analysis. If the reinforcement is an extensible type, this is for the case of this offset being more than the width of the Rankine active wedge at the top of the respective wall, and our particular case is in between this pure vertical or purely independent walls. It is somewhere in between, and so here we need to consider different type of rupture surfaces as shown here. This is for inextensible type reinforcement, that is the steel strips and steel grids, and then this is for the extensible type reinforcements. And there are some guidelines on how to estimate the pressures that are transmitted to the bottom tiers from the upper from the soil in the upper tier, and this is these are all some equations that are given in different codes, and this is from Federal Highway Administration guidelines, and similar guidelines are also given in the NCMA, and it is very easy to write an Excel program to calculate the additional pressure that we have from the upper tiers. So, coming back to the practical construction aspects, the general site conditions are shown here. Actually, this is the old masonry wall that was built along the Ghat road to guide the traffic, and the height, you can see it is very huge, very highly varying, and this is the general condition at the site, and then here you can see the large height difference. Is actually our base is the ground level is somewhere in here, and the top of the hill is about here. That is, at this level the parking space is going to be provided. So, that means that this much height of the soil has to be filled by some means, and the type of facing system that was adopted was a modular block facing. This is a typical rockwood type block, and this block, it has a length of 400 millimeters and the height is 200 millimeters and this depth is 250 millimeters, and this particular block is made of M35 grade concrete by cold pressing process. We just simply take the mold and then prepare the concrete as per the mixed design, and then just simply pour it and then press it to form this block. And the cross section of the 22 meter high wall is shown here. This is built in 2 tiers. The bottom tier is about 12 meters and the top tier is about 10.5 meters, and this offset is 5 meters, that is sufficient to provide a staging for construction purposes and for other aesthetic purposes. And the length of the reinforcement that was designed in the bottom tier was 10.5 meters and the upper tier is 7.4 meters, and the total number of reinforcement layers in the bottom tier are 29 and the upper tier are 18, and as you can see at the bottommost the vertical spacing is very low, and as we go up the vertical spacing increases, and as per the NCMA guidelines, the maximum spacing between the horizontal reinforcement layers should not exceed the height of 3 rows of blocks. In this particular case, the height of each block is 200 millimeters. So, that means that maximum spacing that we can provide is 600 millimeters. So, the spacing although the design spacing comes out higher, the maximum vertical spacing was limited to 600 millimeters, and this is how the reinforcement layout was designed. The bottom tier was provided with a geocomposite having an index tensile strength of 200 kilonewtons per meter, that is the index strength that we determine from short term tensile strength or quick loading test, and the spacing is sorry, it should be 0.4 0.2 meters up to 1.6 meter elevation. The spacing is 200 millimeters, and between height of 1.6 to 6.8 the spacing was 400 millimeters, and then from 6.8 meters to 12 meter elevation the vertical spacing was 600 millimeters, and in the upper tier all the reinforcement layers were provided at 600 spacing, and from a height of 12.2 to 12.8 meters the PEC 200 geocomposite was provided. This number 200 indicates the tensile strength, the index tensile strength, and the PEC 150 having an index tensile strength of 150 kilonewtons per meter was provided between heights of 12.8 to 15.8 and 100 between 15.8 to 17.6 and 75 up to 20 meters height, and beyond 20 meters height PEC 50, that is having a tensile strength of 50 kilonewtons per meter was provided up to a height of 22.4, and beyond this height there was some other finishing heights about another 400 millimeters. And this is how the entire construction started. The construction starts by leveling the ground and preparing the base, and in this particular case, because the subsoil was hard stratum, hard rock at a very shallow depth of about half a meter. So, there was no ground preparation required, and at the bottom you level the ground, and then at the bottommost this stone aggregate that meets the drainage requirements at the place were placed, and the gradation of this the stone aggregate meets the highway requirement, highway standards given by IRC and then the Ministry of Surface Transport. That is mainly to allow the rainwater to dissipate. Then after we place this the stone aggregate, we assemble the facing blocks, and they are just simply placed along the row and along the height without use of any cement mortar, and then periodically there are some outlets given for the rainwater to flow out, and you can see these blocks, then the reinforcement layer, and this is the type of block that was used, and you can see the shear key. Basically that shear key sits in the opening between these two adjacent blocks, so that there is some shear interlocking, and in the construction each of these the upper blocks, they will have an offset of about 10 millimeters from the blocks below, so that there is a natural batter that is given, and the placing of the blocks is very simple. We just simply bring them and manually place them at the site after spreading the reinforcement layer. And the compaction was a major problem at this place because you cannot bring in the standard 10-ton vibro rollers because of the access difficulties. So only a lightweight roller could be brought in, and the compaction with this may not be as good as what we get from the standard 10-ton roller. So it had to be constantly monitored, and the number of passes that we give with this small roller are much higher compared to what we have with a heavy roller, and this is the best that could be done at this place because there is no other access. And this is actually, this picture shows the constraints of the place. This is the construction area. There is one building here, then there is another building next to this, and this entire soil entire area is the construction area, and you can see here this is actually, this is the building that is just next to this building, and there is a gap of about hardly 1.5 to 2 meters only for the people to walk, and there is no other possibility for bringing in equipments. And you can see this chimney drain, what we call as a chimney drain, because as the soil is placed just at the back of the soil, adjacent to the hill, 200 to 300 millimeters thick aggregate layer, vertical layer was provided. The purpose is, if there is any surface runoff, it should flow along this chimney drain and then flow out from the bottom. And because of the difficulty of bringing in the soil directly into the construction site, it was dumped from the ghat road. It's actually the ghat road, as you have seen in the very first slide, it is already existing, and all these lorry loads of material was taken to the top of the hill, then it was dumped from the top, and here you can see this lorry dumping the stone aggregate. Similarly, the sand and then the gravel fills were dumped, and then at the place it was the soil, the gravelly soil and the sand were mixed manually before placing them. And the compaction control is a very important aspect in any of these constructions, especially in the retaining walls, because if the compaction is not adequate, there will be higher lateral earth pressures, at this particular site, each layer of the soil compacted was adequately checked by taking core samples, by sand replacement methods. The compaction quality was determined, and only after the compaction quality was found to be adequate, then you go and place the next layer of soil, and the soil was compacted in thin layers about 100 to 200 millimeters thick, because the compaction equipment is a very lightweight equipment. And it is also very important that during the construction, if there is any rain, we should not allow the rainwater to percolate, because during the construction the soil is just compacted and it may not have gained strength, and then if you allow the rainwater to go in, it is very difficult to get adequate compaction quality, because as you know, the wet soil is very soggy and it will not be, you cannot really compact it. And so at this particular place, even during a small drizzle, the entire soil area was covered with polythene sheets, so that the rainwater does not penetrate into the soil. And here you see another picture. Is actually along the length of the wall, we provide another drainage pipe. Although we place the drainage aggregate, is actually the drainage pipe is, the purpose of this drainage pipe is to collect the runoff water and lead it safely away from the reinforced fill. And this is the close up view of the chimney, and you can also notice that this the aggregate was placed along with a filter fabric, because during the service life, the aggregate layer that we are providing, it should not get choked with fine particles. And so this this filter fabric, it is a non-woven filter fabric, it is provided so that the fine particles does not infiltrate into the drainage blanket. And you can see the pictures of the construction. This is at 3 meters height, and then this is at 19 meters height, and you can see that the reinforcement layer is not provided horizontal. Is actually a kink was given, so that there is a good interaction between the soil and the reinforcement. Is actually it's a kink. Instead of placing the reinforcement horizontal, the reinforcement was placed horizontally, then it was brought up by about 10 millimeters, and then it was locked into these blocks, and the inside of these blocks was also filled with the stone aggregate, so that there is a good interaction between the blocks, the soil, and then the reinforcement layers. So here you can see this stone aggregate placed in the blocks, and you can see another view of the wall being constructed. You can see the clear picture, the vehicles dumping the soil from the top, and this is another view of the wall during construction. It is actually this notice the existing building is very close, it is hardly about 1.5 to 2 meters gap, and in spite of that this wall could be built, because the soil was dumped from the top, and then the entire construction was made using modular blocks, each weighing about 30 kg. So, it could be easily carried by people and placed at the site. And this is the completed 22 meter high wall. The bottom one is about 12 meters and the top one nearly 10.5 meters. And this is the view from Krishna river, from the middle of Krishna river. You can see how densely the entire area is populated. Too many buildings, too many residential buildings, too many buildings associated with the temple, and this is the footpath that is used by pilgrims to go up to the top of the hill. And once again you can see the fragile nature of this hillock, just too many joint planes and then fissures. And here we can see the additional space that was gained for construction of the road. The previous road was only this wide, about 3 meters. Now it is another 20 meters is added. So you can build a nice two-way road instead of one-way road. And you can see another picture of the same thing. It is a very wide area for our construction purposes. And the other wall that is just adjacent to 22-meter high wall is the 44-meter wall, which is built in 4 tiers. Each tier, the bottom tier was about 12 meters, and this is also another 12 meters, and this is 11 meters, and this is about 10 meters high. And this is the graphical representation of the system. Actually, this is all the soil fill, and this is the filter that was provided. And the design codes are a bit hazy about the design of tiered walls, and one suggestion made is although the entire system was designed as a retaining wall, we have to check for the global stability by taking different slip circles passing through both the reinforced fill and then the backfill, and make sure that there is adequate factor of safety under the worst case scenario, that is with seismic factors. And Vijayawada being in the zone 3 area, appropriate seismic factors were considered in the design. And here you see the result from the slope stability software that indicates the different types of safety factors that were obtained. The blue color indicates that the factor of safety is greater than 2, and this red color there is a patch that is actually very close to our active rupture surface. It has a factor of safety of about 1.35, and this yellow color has a factor of safety of 1.6, and this 1.35 is after including the seismic factors in the analysis. And this is the same analysis done with some other software. The analysis were done with 2 different softwares. The previous one was done using a program called RISA that is recommended by Federal Highway Administration, and this analysis is done using Talren. This is also a very popular slope stability analysis software that can incorporate the different construction methods like the soil, reinforcement layers, and then the facing elements and so on. And here we see that the factor of safety, this is actually the critical surface for the 2-tier wall is going behind the reinforced fill, and the factor of safety is about 1.39, the minimum factor of safety, and if you take a circle passing through this, it is much higher. And this is for the 4-tier wall. The factor of safety is about 1.47 after considering all the surcharge loads and then the seismic loads and so on. And this is another result from the same analysis, and this shows the overall ground conditions. This is at the bottom of the slope, and then the soil is being built up to this level, and this is the construction stage. Is actually this long wall all around, then we place the soil, and this is the finished wall. This is the 4th tier, the upper tier, 3rd tier, 2nd tier, and the 1st tier, and this is the view of the bottommost wall. Actually it is perfectly straight, absolutely no lateral deformations or anything, or no settlements, because the foundation soil is extremely strong. but unfortunately there were some problems, because some part of the wall is directly resting on the hillock, whereas the other part of the wall is resting on the soil. And in the hindsight, there should have been a vertical joint between the two parts of the wall, but because the vertical joint was not provided, there were some differential settlements, and you can see the crack that is formed, and some part of the soil started bulging out because of the differential movements. And then some contractor has started installing soil nails, but then unfortunately these nails were placed very close together, and that has resulted in some of the blocks coming out. And so there were some problems, otherwise the entire system is stable, and there is, you can see one modular block that has come out because of driving of 20 mm soil nails driven at a horizontal vertical spacing of nearly 200 millimeters. That is too much of nailing in this soil conditions. And at the top of the hill at 44-meter height, there were some subsidences of the order of about 500 millimeters, and that is mainly because some part of the soil was not compacted adequately, because the entire compaction was done using lightweight rollers. So, that was not adequate, and so after about 6 months of subsidence, the entire top soil, the top concrete was removed, the top soil was removed, then it was replaced with pond ash, and then resurfaced. And here you see at the third tier level there were some differential movements, once again because part of the wall was resting on the hill and part on the lower tier of the walls. And then some areas the compaction was the construction proceeded during the rainy season, where there were some soft patches, and because of that there were some settlements, and you can see the effect of that local subsidence. The wall has moved inward, and then there is some small bulging in one of the corners, but otherwise the entire wall is stable, and it has been there for almost 4 years without any major substantial problems. And now these the entire parking area is open for traffic. You can see this entire area was gained. This is about 22 meters, and this length is nearly 100 meters. So, you can imagine how many cars and how many vehicles we can park in this additional area. And we need to use a lot of test data, and one important test data is on the connection strength between the facing blocks and the reinforcement. The schematic for doing these laboratory tests is shown here, and this is the plan view, and this is the photograph of the load tests being done in the laboratory, and this is the typical data for tests on 75 PEC 75, that is having tensile strength of 75 kilonewtons per meter, and you can see that the peak load capacity, the connection capacity is only about 29. So, we can only utilize a small fraction of the tensile strength of the material for our design purposes. And along with this construction, number of rockfall protection measures had to be taken. Here you can see an anchor that was installed and that was bolted down to stabilize the rocks, and some rock netting was given along with nails. And some of the conclusions that we can draw from this case study is that the reinforced soil wall technology is very widely used in India, and the applications for these constructions include approach roads, and then bridge abutments, coastal erosion protection works, and so on. And even small companies, they are able to take up these major projects and come out with successful designs and successful constructions. and this particular reinforced soil retaining wall has saved lot of time and money, because the 22-meter high wall was built in less than 6 months, whereas the 44-meter wall was built in about 1.5 years, and it created large usable space for traffic and parking at the hilltop. So, thank you very much.